Assalamu alaikum students. I welcome you all to this new session. We are still discussing absorption refrigeration system and we have discussed different components of it, the four major components: absorber, generator, condenser and evaporator. And then we had discussed that it has also a pump and a expansion valve. So now we want to look at how to calculate, and we have also seen how to find out the enthalpies of them. So how to find out the important enthalpies. Now in this lecture we are going to cover COP of ideal absorption refrigeration system, and then mass flow rates means the mass balance for the solution and the salt. And then we will look at thermal analysis of simple absorption system. We will consider a couple of examples where we will try to find out the enthalpy of the refrigerant and enthalpy of the solution using those two diagrams that we had discussed previously, that is PXT and HXT. So moving on. So as I have been telling you from last time that we are going to discuss the COP of the ideal absorption refrigeration system. This is similar to what you have studied in your thermodynamics about about proving that second law of thermodynamics, Kelvin-Planck statement and process statements, they are equivalent. So if you violate one, you will violate the other one. This COP of the ideal absorption refrigeration system is explained in the same manner. So here we consider the maximum COP of an absorption refrigeration system is determined by assuming that the entire cycle is totally reversible. That is, the cycle involves no irreversibilities and any heat transfer is through a differential temperature difference. So this is an ideal reversible system that we are considering. So here we have a source at a temperature of Ts, and we have a sink or the environment where the heat is being expelled at T0. So if this is a reversible Carnot heat engine, then whatever energy is supplied to it, if this is a reversible Carnot heat engine, then whatever energy Qgen supplied to it, it will convert all of it to the work W, which will be equal to the efficiency eta of the reversible engine into the Q heat that's been supplied to it. And if we supply this reversible work into the reversible refrigerator, then it should, with the help of that work, it should pull some of the energy from the low temperature medium, that is refrigerated space, and throw it in the environment T0. So it can pull energy from TL and throw it in the T0. The refrigeration system would be reversible if the heat from the source Qgen were transferred to a Carnot heat engine. So this is our reversible Carnot heat engine, and the work output of this heat engine, which would be W into eta thermal reversible into Qgen, is supplied to a Carnot refrigerator to remove heat from the refrigerated space. Then in this case, QL will be equal to the work supplied to your reversible refrigerator into COP of the reversible refrigerator. From the definition of COP is equal to QL upon W, from there we can say the QL must be equal to W into COP R reversible, and W is eta thermal reversible into Qgen, the heat supplied to the reversible engine, multiplied by COP R reversible. Then the overall CPU of an absorption refrigeration system under reversible condition would become, so now we want to calculate the COP of the reversible refrigerator. So W dot was eta Carnot into QG. Okay, so eta Carnot, if it's a reversible engine, can be represented in terms of temperature, that is Ts minus TO or T environment should be divided by Ts should be equal to Q dot G. Same as we have a COP of a Carnot refrigerator, TL upon TS, TL upon TH minus TL. Similarly here, for a Carnot heat engine, we can write TS minus T0 upon TS into QG. So, and then QL is equal to COPR of the Carnot into W. Okay, and then we replace COPR of the Carnot. The ideal COP value will be TL divided by T0 minus TS. So TL is the low temperature divided by T0 is the high temperature minus TL. Okay, so these are from the definition. This is from the definition. This equation we got the eta Carnot. This is the equation in terms of temperature for eta Carnot, and this is the equation for COP Carnot, COP refrigerator for Carnot. Okay, so this is QG and this is W dot at the end. So if we want to find out the COP of the absorber reversible absorption system, absorber refrigerator system, COP ABS REV, then it will be equal to, by definition, it is Q dot L upon QG. We want to find out QL is this value, this temperature ratio into W dot, and then QG will be this temperature ratio into QG. W dot will be QG we have to find out from here, QG from here. So it will be W dot divided by this temperature ratio. So if you do that, you will get this equation, W dot and W dot, this one will cancel out, and you will get a temperature ratio. This can also be written as TS minus TO for the engine side divided by TS, T source and T sink, okay, multiplied by the Carnot refrigerator efficiency equation. Okay, so this is the heat engine, Carnot heat engine efficiency. So eta thermal reversible, and this is the Carnot refrigerator COP. So COPR into Carnot. So that's how COP of the absorption refrigeration system will be equal to thermal efficiency of the Carnot engine multiplied by COP of the Carnot refrigerator. So this is one of the article that we had to cover. Okay, so moving on to our main topic of doing thermal analysis of the vapor absorption refrigeration system. So calculation of the mass flow rate in the absorption cycle. We are going to explain it with the help of an example here. See, the first stage in analyzing the simple lithium bromide water absorption refrigeration cycle can now be performed by using the property data presented in figure 17-5. So that 17-5 and 17-8 are the two figures, PXT and HXT diagram. Example 17-2 from your Stoker book. Compute the rate of flow of refrigerant, which is water, through the condenser and the evaporator in the cycle shown. So mass flow rate, determine the mass flow rate. If the pump delivers 0.6 kg per second and the following temperatures prevail. So generator is 100 degrees centigrade, then the condenser is at 40 degrees centigrade, and the evaporator is 10 degrees centigrade, and the absorber is 30 degrees centigrade. We know that the condenser and the evaporator has pure water in it, water vapor or liquid water. So these two has pure water and these two have solution. Okay, so the solution temperature we can measure, and the pressure of the generator will be equal to the pressure of the condenser, which has water in it or water vapor in it, at 40 degrees centigrade. Saturated vapor or saturated water. So this saturated vapor pressure at 40 degrees centigrade of water, whatever it is, that will be the pressure in generator. Similarly here at 10 degrees centigrade saturated vapor, whatever the vapor pressure of the water here, that will be the same pressure here in the absorber. So that's how we work. We figure out what is the temperature of the solution, we can measure it. What is the temperature of the solution in the absorber, we can measure it. What is the pressure? It is the same as in the condenser and in the evaporator. So generator pressure will be equal to the condenser pressure, or I should say other way around, because we can find out what is the condenser pressure. It will be the saturated vapor pressure of pure water at 40 degrees centigrade, and this will be saturated water vapor pressure at 10 degrees centigrade. We can figure out what is the pressure here, saturated pressure here, from the steam table, and we can use it to say that the generator must have the same pressure as the condenser and the absorber must have the same pressure as the condenser, because they are both interconnected by the pipeline. Okay, they cannot have two different pressure. At equilibrium they will have the same pressure. So moving on, the computation of the mass flow rate incorporates material balance using applicable concentration of the lithium bromide in the solution. Two different pressure exist in the system, one low pressure, one high pressure. So your evaporator and absorber are at low pressure, and after the pump, the generator and the condenser has the high pressure. While the low pressure prevails, since a saturated condition of pure water prevails in the condenser due to simultaneous existence of liquid and vapor, the condensing temperature of 40 degrees fixes the pressure in the condenser. Okay, which is at 40 degrees centigrade. If you look up the steam table, it will be 7.38 kilopascal. This will be also the same pressure in the generator. For similar reasoning, the evaporator temperature of 10 degrees establishes the low pressure of 1.23 kilopascal in the evaporator. Now, figure 7-7 is a skeleton PXT diagram extracted from 17-5 to display the state points of lithium bromide solution. So we have lithium bromide solution in the evaporator and in the condenser. Low temperature in evaporator, high temperature in the condenser. So we know the solution temperature and we know the pressure in there. So we can find out what is the concentration using figure 17-5. We know that the generator is 100 degrees centigrade, pressure is 7.38, and we know the absorber is 30 degrees centigrade and the pressure is 1.23 kilopascal. So the same diagram, this is a cutout from the 17-5 and this is the whole 17-5. So I have drawn a line of evaporator line which is at 10 degrees centigrade. Okay, so this brown line is the evaporator line, 10 degrees centigrade, temperature on the left hand side, and the pressure, corresponding vapor pressure, is 1.23. And similarly for condenser is at 40 degrees centigrade and the saturation pressure of water at 40 degrees 7.38. So these two lines are showing the temperatures of the evaporator and condenser. So whichever line of solution in the condenser, in the generator, is 100 degrees centigrade. So wherever it crosses our 7.38 pressure line, that's the point, that's the state of concentration in the generator. So the generator concentration will be, if I draw the vertical line from here, I can read the value of the lithium bromide in the solution by reading this thing. So which I am saying it is 66.4%. Similarly, this is the evaporator line, and this point, this is the absorber solution temperature. Okay, 30 degrees centigrade. The green line is 30 degrees centigrade, and it is crossing the evaporator pressure line at this point. So whatever is the concentration by drawing the vertical line, that is the concentration in the absorber, which is 50%. So that's how we determine, by knowing the pressure and the temperature of the absorber and the generator, we can determine what is the concentration, X value there, the value of the X concentration. X concentration we are representing here with X. So that is 50% and 66.4%. So now we know the percentage concentration of lithium bromide, or we know the concentration and we know the solution temperature. We can use the next diagram, which is HXT diagram, to find out H, the enthalpy value. So we want to do that. Let's look at this. Okay, we are done with this one. We understand how to get this value, the concentration. We understand how to get the concentration. Now we want to find out what is the enthalpy value. So the solution leaving a component is representative of a solution in the solution leaving a component is representative of the solution inside the component. So what does that mean is that whatever solution here, whatever solution here, 0.2, is leaving from the generator, that should have the same value as what is inside the generator. So if you know the generator is 100 degrees centigrade, 0.2 is 100 degrees centigrade. Similarly here, whatever is leaving the component, 40 degrees centigrade, so 0.4 will be 40 degrees centigrade. And similarly here, 5 should be at 10 degrees centigrade. Okay. The solution leaving a component is representative of the solution in the component. So the state points of the solution at point 2 leaving the generator is found from figure 17-7 at the intersection of the solution temperature of 100 degree and 7.38. This concentration is X2 of 66.4%. So the solution temperature and the pressure temperature. Okay. So wherever they cross, that is the state of solution in that container. So this was the generator. So generator is 66.4%. Whatever solution is leaving the absorber, or the solution leaving the absorber at temperature of 30 degrees centigrade and pressure of 1.23 will have X1 value of 50%, as I explained you in the diagram. The two mass balances can be written about the generator. Now we want to do the mass balance about the generator. So we are in the generator, m.2 and m.3, they are leaving from the generator, and m.1 is entering the generator. So let's look at that. This is the generator. So this is the pump which is sending lithium bromide solution to the generator. So m1 is coming into the generator, and then from the generator this m.3 is leaving towards the condenser, and m.2 is leaving towards the expansion valve. So these two, m.2 plus m.3, which is leaving the generator, should be equal to m.1, which is coming into it, because it's a steady flow process. So that's what we wrote. 1.2 plus m.3 is equal to m.1, and this is given in this example of 0.6 kilogram per second. And lithium bromide balance, whatever lithium bromide is leaving is m.1 into x1, and whatever is coming back from the generator into the absorber is m.2 into x2. So if you look it up here, see, m.1 and x1, x is the concentration or percentage of lithium bromide in the solution. So m.1 x1 is the mass of lithium bromide which is leaving, and m.2 x2 is the mass of lithium bromide which is entering the absorber. So they should be equal if it's a steady flow process. Okay, steady state and steady flow process. So that's what written here. Lithium bromide balance, m.1 x1 should be equal to m.2 x2. Now we know the m.1 is 0.6, it is given. X1 we found out from the graph, from the pxt graph, and here m2 we don't know, but x2 we know it is 66.4% from the pxt graph. Okay, so now if we solve it, we can find out what is m.2. Once we know m.2, we can replace it here, and we can find out what is m.3. So m.3 is 0.148 kilogram per second. So now we know all the mass flow rate. The mass balance is done. Okay, approximately 4 kilogram of solution is pumped for each kilogram of refrigerant water vapor developed. Okay, now thermal analysis, that is to find out the enthalpies. So it is previous example was 17-2, this is 17-3. For the absorption system of example 17-2 shown in figure 17-6, compute QG, that is energy in the generator, QA, energy of the absorber, QC, energy of the condenser, and QE, energy of the evaporator, and the COP of the system. So the flow rates and the solution concentration have already been determined. So we know what is m.1, what is m.2, and what is m.3. So m.3 should be equal to m.4 and m.5. let's look at the diagram so you understand. They will be equal. M dot 3 should be equal to M dot 4 and M dot 5. Whatever is coming out from the generator is the same thing which is going into the condenser. It is same thing which is coming out of the condenser, and it is going to the evaporator, and it is the same thing which is same amount which is coming out of the evaporator. That's why we say M dot 3, 4 and 5, they are same. Those mass flow rates are same. M dot, where is that? Here you go. M dot 3, 4 and 5, they are 0.148 kilogram per second, and x1 is 50% and x2 is 66%, as we determined previously. The enthalpies of the solution can be read off figure 17-8. This is the HXT diagram, this diagram. So in the generator we have 100-degree solution, and we know the concentration of it is 66.4%. So the red line is the solution temperature line, and the green line here is the concentration line of the generator. So wherever they cross, that is the state of the generator, and we can draw a horizontal line to find out what is the enthalpy value there. So that enthalpy we read as minus 52 kilojoule per kilogram. Minus 52 kilojoule per kilogram. Why minus? Because of the datum that we have selected. That is, water at 0 degree has 0 enthalpy, and lithium bromide salt at 25 degree has 0 enthalpy. So based on that we develop a scale. That scale is telling us that it is minus 52 kilojoule per kilogram. Otherwise you can argue that it is a scalar value, so why does it has a minus sign in front of it? But it is minus because of our datum line. The way we have selected the datum. So that is the value of the enthalpy of in the absorber, in the generator, I'm sorry. So we figure out that H2 at 100 degrees centigrade and x of 66 or minus 52. So similarly we can find for the absorber also. Absorber has 30 degree solution temperature, and we found out previously that its x value, this concentration, is 50%. So if we draw it on the HXT diagram, so the yellow line is the solution temperature line here, that's 30 degrees centigrade, and this brown line is showing the concentration of the lithium bromide in the absorber. So wherever they cross, that's the point which is the showing the enthalpy of the absorber. So we draw a horizontal line from here, and from here we can see that it is less than it is more than 160. So I read it as minus 168 kilojoule per kilogram. Okay, so those are the two values of the solution. Now we want to find out the enthalpy of the water, pure water in condenser and evaporator, that we can find out from the steam table. So moving on, here you go. So the enthalpies of water, liquid and vapor are found from table A1. So H3 is saturated vapor at 100 degrees centigrade. H3 is saturated vapor at 100 degrees centigrade. Okay, so H3 at 100 degrees centigrade saturated vapor. If you look up the table, here is the table. 100 degrees centigrade vapor 2676. So that's the value I have copied there. This value here. Okay. Look it up. It's 100 degree centigrade. So it will be 2676 from the table A1. Okay. Similarly, H4 is H of saturated liquid at 40 degrees centigrade. So H4 is coming out of the condenser. After condensing, the water vapor is condensed in the liquid form. It is coming out here. So saturated water, saturated liquid at 40 degrees centigrade. Saturated liquid at 40 degrees centigrade. 40 degrees centigrade, saturated liquid, 167.45. So that's the value, 167.45. And then H5 is H of saturated vapor at 10 degrees centigrade. From the table you can see that it is 2519.9, so I have rounded it up as 2520 2520.0 kilojoule per kilogram. If you look it up in the table, at 10 degrees centigrade, it is 2519.9. So I have rounded off as 2520. So this is that value. Okay, so now we know the enthalpies of all the important points, 5 points maybe. Okay, so this is the value that I have taken. All right. So next we want to do the energy balance. The rates of the heat transfer at each of the components can now be computed from the energy balances. So we want to do energy balance around the generator, around the condenser, around the absorber, and around the evaporator. So energy balance around the generator first. So what is coming into the generator is m dot 1 H1. So m QG, the heat which is supplied to the generator, plus m dot 1 H1 is the solution which is coming in from the absorber to the generator, should be equal to m dot 3 H3. It is the solution which is leaving the generator towards the condenser, plus m dot 2 H2. This is the mass or the solution which is leaving the generator towards the expansion valve. So these two, m dot 3, m dot 2 are leaving, and then m dot 1 and QG is the heat energy which is coming into the generator. So if you balance it, we can find out the QG. The final equation for QG will be QG is equal to m dot 3 H3 plus m dot 2 H2 minus m dot 1 H1. Substitute the values, so you get your QG as 473.3 kilowatt. Similarly QC, similar energy balance. Okay, in the condenser, we have only what is coming in is in the condenser is m dot 4 H4. Is that coming in? Come on, let's see. In the condenser, m dot 3 H3 is coming in, and m dot 4 H4 is leaving, and QC is also leaving. So these two, QC plus m dot 4 H4, should be equal to m dot 3 H3. Here you go. QC is leaving plus m dot 3 H4. These two should be equal to m dot 3 H3 which is coming in. So whatever energy is entering should be equal to whatever energy leaving that component. So we can find out QC, substitute all the values, you will get 371.2 kilowatt. Similarly around the absorber, okay, we do a energy balance. Whatever energy is coming into the absorber and whatever leaving it, you balance it, you will finally get this equation. QA is equal to m dot 2 H2 plus m dot 5 H5 minus m dot 1 H1. Substitute all the values, you will get QE as 348.2 kilowatt, and then finally you can calculate what is the COP of the absorption system, which is QE divided by QG. QE is the refrigerating effect produced, divided by QG is the amount of energy required in the generator. So if we divide the two, we get 0.736 value. Okay. Next is the example where we have incorporated a heat exchanger into our vapor absorption system. So basically this is the same example that whatever we have been doing before, but we have just added the heat exchanger into it. So when we add the heat exchanger into the system here, so our numbering will slightly change. Now 1 is same, but 2 is after the generator, and 3 is after 2 is after the heat exchanger, 3 is after the generator, 4 is after the heat exchanger of the solution, and then 5 going from condenser, from the generator to the condenser. So the this heat exchanger did not affect the pure water side, that is, it did not affect the condenser and the evaporator. So previously we had H3 here and H4 here and H7 here, so that will be H5, H6, and whatever value we have found out before from the table, we are going to use the same value here, because these are not changed. Only value change will be here in 2 and 3 and 4. So we have to recalculate those, otherwise these are same. So certain quantities are unchanged from example 17-2 and 17-3. So the mass flow rate m dot 1 and m dot 2 will be same because it was given to us 0.6 kilogram per second. M dot 3, m dot 4 will be same. M dot 3, m dot 4 will be same as we figured out before. So it will be 0.452, and m dot 5, m dot 6, m dot 7 will be 0.148. This was m dot 3 previously. So this mass flow rate will be same. This is, we are copying from the previous example. If you look it up, you will see that, okay, this makes sense. How this should be the same thing, okay? Because only thing we have added is a generator here. The other values, the absorber, generator, condenser, evaporator, their temperatures and solution solution temperatures are same. Okay, moving on. The enthalpies that remain unchanged are H1 is minus 168, is still the same. H3 is minus 52, is still the same. Okay. H5 is 2676, maybe had a different number before. H6 is 167.5 and H7 is 2520. So previously I think it was like H5 before. Only the number prefix has changed. The suffixes have changed, but the value is same. So if you compare before, the previous diagram with this heat exchanger added diagram, then you will see that these values are at the same location as it was before. Okay, and they did not, the heat exchanger did not affect them, so their value will be same. The heat transfer rates at the condenser and the evaporator remain unchanged because the heat exchanger is not affecting your condenser and evaporator, so their values has been copied here. Okay, now considering the heat exchanger, what difference it will make. So the temperature of the 50% solution leaving the heat exchanger at point 2 is 52 degrees centigrade. This is given. This temperature 52 degrees centigrade after the heat exchanger, it is given. And its concentration is 50%. Why? Because this is the solution which is leaving the absorber, and we found out that the absorber concentration is 50% previously, and the condenser, and the generator concentration was 66.4%. That will not change because solution temperature and their concentration will not change. Only the temperature exchange here will cause, heat exchange here will cause the temperature difference. Before the solution leaving here was 30 degrees centigrade and entering in the generator at 30 degrees centigrade, but now it will enter at 52 degrees centigrade. Okay, so that is the difference. So at 52 degrees centigrade, because we know the solution at point 2 is, the temperature is given 52 degrees centigrade, and X value we know it is the same solution which is coming from the absorber at 50%. So if we know the concentration and if we know the temperature, we can use the HXT to find out what is the enthalpy value. So I have marked it here, the enthalpy value of 120 at point 2. We are talking about after the heat exchanger. So after the heat exchanger, the temperature was 52 degrees centigrade. This is the solution temperature. So 52 degrees centigrade solution temperature will be above the 50 degrees centigrade but below the 60 degrees centigrade solution temperature. So this yellow line is between those two, showing at 52 degrees centigrade, and this is the concentration of that solution. And okay, so once we know these two, the yellow line and this brown line, so wherever they cross, that is the state of point 2. At that point the enthalpy is 120 kilojoule per kilogram. So that's how we find out what is H2 value. Okay, so the H2 value written here, H2 value written here is minus 128. That's how this 128 came. Okay, now we want to do a heat balance for the heat exchanger. The rate of heat absorbed by the solution passing from the absorber to the generator is, so heat absorbed by in the heat exchanger by the solution coming from the absorber. So the mass flow rate was m dot 1 and it was coming at H1, the first state, and then H2 minus H1 after the heat exchange. Before the heat exchanger was heat exchanger was H1, and after the heat exchanger it was H2. So we can figure out what is the amount of heat exchange in the heat exchanger, which is 28.8 kilowatt. Similarly, this is the going from absorber to the generator. Similarly, we can do an energy balance. This amount of energy is absorbed by the solution which is coming from the generator to the absorber. So whatever energy gained here in this pipe, the same amount of energy is lost here by this pipe. this pipe which is coming from generator to the absorber, and this pipe which is going from absorber to the generator. So energy lost here will be energy gained here will be energy lost here. So from that idea we equate, since the same rate of heat transfer must be supplied by the solution that flows from the generator to the absorber, so we equate this amount to the other side now, m dot 3, H3 and H4. So this is how we find out what is H4. So H4 is 116 minus 116 kilojoule per kilogram, the enthalpy of point H4 of this point right after the heat exchanger. Okay, so where is this H4? The state of this H4 we can locate it in the graph, because we know its temperature. We want to find out the temperature of point 4. So we know the concentration of 0.4 is the same as what is the concentration in the generator, which was 66.4%, this green line, and the enthalpy value of H4 we calculated it was this green line, so that is minus 116. We calculated this amount, so the pressure, the solution temperature must be this blue line. So we draw a line which cross these two green lines, whatever solution line is crossing these two blue line, that is the temperature of that solution. So we estimated it to be 64 degrees centigrade. Where is that? Okay, this is it. Okay, these are the diagram. Okay, it's right here. Figure 17-8 shows that 66.4% solution with an enthalpy of minus 116 kilojoule per kilogram has a temperature of 64 degrees centigrade. The rates of heat transfer in the generator and the absorber can now be computed. So same energy balance we did to calculate the energy transfer in the generator, okay, and in the absorber. So these are the two new values after the heat exchanger. So COP of the system is now 0.783 with the heat exchanger. Previously it was 0.736. The new value is higher. The COP is an improvement over the value of 0.736, which was before the heat exchanger. Now with the heat exchanger you get a better COP value, but it's still less than 1. Applicable to the simple system without a heat exchanger. Okay, I think we will not be able to finish this second example here, but okay, what should we do? Okay, let me stop here and then I'll pick up from in the next session for the second example, and then we will have probably one more article to go over. Okay, I thank you very much, and if you have any question, if you do not understand anything, you can note down the slide number and then ask me, then I'll try to answer you this. But these are fairly easy. Vapor absorption system is fairly easy system, and the calculation of it, thermal analysis of it is fairly straightforward and easy. So if you practice, I'm sure that you can learn it easily and understand it and solve the numerical really easy. Thank you, sir. Thank you very much.